what's the probability of exactly k favorable outcomes if an experiment is conducted n times? Let us take a simple, for our understanding, example. What's the probability of getting 3 heads if you toss 5 coins? So if a coin is tossed 5 times, what is the probability that I will get exactly 3 heads? If I am to get exactly 3 heads out of the 5 tosses of a coin, effectively I am looking at 3 H's and 2 T's. If I am looking at 3 H's and 2 T's, the arrangements, the number of arrangements in which I can get 3H and 2T, this will be 5 factorial upon 3 factorial 2 factorial. I am basically arranging 3 H's and 2 T's divided by total possible outcomes, because for each throw there are 2 possibilities, HT, 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 HT. So total possible outcomes would be 2 to the power 5. So this should generally be my answer, 5 factorial upon 3 factorial 2 factorial divided by 2 to the power 5. Alternately, out of the 5 places, you choose the 3 places where you will get a head. For the remaining places, you will get a tail. So 5C3 divided by 2 to the power 5. This can be one way of looking at it. Another more apt way of looking at this problem would be, if out of 5 experiments I am looking at 3 heads, which is my success, the probability of each head is equal to 1 by 2. So out of 5 I need to choose 3 places where I need a success, multiplied by the probability of the event happening to the power. So let us say this is 1 by 2, so 1 by 2 to the power 3 into, in the remaining experiments I should not get this, so the probability of not getting a head in the remaining ones, if head is 1 by 2, not head is also 1 by 2, so into 1 by 2 is square. This is my answer. In general, out of n experiments, the probability of exactly r successes is NCR, the probability of success in one experiment to the power r into 1 minus p to the power n minus r. If let's take another example, what's the probability of getting exactly 3 5s if I throw a dice 5 times? So I'm throwing the dice 5 times. I need exactly 3 5s. If I need exactly 3 5s out of 5 experiments, exactly 3 into the probability of getting a 5 in any experiment is 1 by 6. 1 by 6 to the power 3 into 1 minus 1 by 6 is 5 by 6. 5 by 6 remaining 2 experiments is square. So the probability of my not getting a 6 in the remaining experiments. The idea is that out of the n places, we choose the r places where we want a success, and at the same time we also need to make sure that at the remaining places we do not get a success, which means that we do not get a 5 in this case or a head in this case. So therefore NCR p to the power r 1 minus p to the power n minus r. So NCR p to the power r 1 minus p to the power 1 n minus r. This is the general formula for getting exactly k favorable outcomes out of n experiments. So that was example 1. Let's look at example 2. You have exactly 100 coins with the probability of a head showing up on a coin. These are not the usual coins, these are biased coins. The probability of head is equal to p. The probability of 50 heads is equal to the probability of 51 heads. Then what is the value of p? If I am looking at the probability of getting exactly 50 heads, this should be equal to 100 C 50 into p to the power 50 1 minus p to the power 50. The probability of getting 51 heads would be equal to 100 C 51 p to the power 51 into 1 minus p to the power 49. If both of them they have to be equal, we can solve this equation. By solving this, we will get the value of p that would be our answer. Let's quickly see. 100 P50, this will become 100 factorial upon 50 factorial 50 factorial multiplied by p to the power 50 into 1 minus p to the power 50 is equal to 100 factorial upon 51 factorial 49 factorial multiplied by p to the power 51 1 minus p to the power 49. So p to the power 50, this becomes p, this whole goes, this becomes 1 minus p. So from here 1 minus p, 100 factorial will cancel, multiplied by 5149. 5149 will be 50 square is 2500. 2500 minus 1 is 2499 is equal to p into 50 factorial 51 into, I'm sorry, this is wrong. So from here 51 and 50 factorial will cancel out, and 49 factorial will go, this will become 50. So from here I will have 51 into 1 minus p is equal to 50 into p. So 50 into p, 51, this becomes 51 comes on this side, this becomes 101. 51 upon 101 is equal to p. So the probability is 51 upon 101. Let's look at the third example. There are 7 people in a room. The probability that exactly 2 of them were born on the same day of the week. So out of the 7 people, exactly 2 people, they have to be born on the same day of the week. So what is this probability? In order to find the probability that exactly 2 of these people are born on the same day, first things first, the total possible outcomes would be 2 to the power 7 to the power 7, because overall there are 7 people. Each person could have been born on any day of the week. So Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, all 7 possibilities are there for each of the 7 people. So 7 into 7 into 7 into 7 into 7 into 7, total possible outcomes becomes 7 to the power 7. The second part I am looking for, exactly 2 of them have to be born on the same day. If exactly 2 of them have to be born on the same day, let us say out of the 7, 2 people who are born on the same day, they can be chosen in 7 C2 ways. Once I have chosen these 2 people who are born on the same day, they have the luxury of choosing the day on which they would like to be born. So person 1 and 2, they are decided. The next person comes, he can be born on any of the remaining 6 days. So the next person will be able to choose from any of the 6 days. The fourth person will come, he can choose any of the days except for these 2 days, because if he chooses this day, then this arrangement of exactly 2 people being born is gone. If he chooses this day, then only one pair condition, that is also gone. So the fourth person, he would be able to choose into 5, next one 4, next one 3, last one 2. So 7 6 5 4 3 2, 7 C2 divided by 7 to the power 7. So this becomes whatever the value this will be, that will be your answer.